Okay, hello. So, as we mentioned, today we'll see applications of thermodynamics to energy science and technology. And we'll see that the majority of uh, electric power generation is relying on power plants. So we need to understand how these power plants operates and how we can enhance their efficiency. And we can sometimes combine several cycles together to get a big improvement in the energy efficiency. So if we want to explore several types of power plant, in this course, we learned that we'll go over several resources of energy, including fossil fuels, coal, natural gas. Then we'll explore renewable resources as solar, hydroelectric, wind, etc. But even if we consider different types of sources, we can, in majority of these sources, we can use them in thermodynamic cycles. That's why it's very important to introduce the main concept of thermodynamics that we'll use in order to calculate efficiencies, in order to study performance of renewable and non-renewable systems. So for example, if we consider electric power generation as example, the following table is summarizing the different types of power plants that are used to generate electricity. So for example, if we talk about coal-fueled power plant, which is a non-renewable source, it's based on the Rankine cycle. If we study a natural gas fueled system, it's based on Brayton cycles that will also be introduced in this chapter. For both nuclear and oil fueled also, which are non-renewable sources, also we are relying on Rankine cycle. So you can see that for the majority of cases, we rely on Rankine cycles. That's why it's a very important cycle, and it's a basic cycle that is really simple. So we'll see together what are its main components, how we can enhance its efficiency, what are the strategies that can be performed to as heat recovery or reheating, etc. What we call cogeneration also, regeneration. All of these ideas can help us into enhancing the efficiency of our system. Even if we rely on, let's say, biomass or geothermal or concentrating solar systems, also all of these, which are renewable sources, are based on the Rankine cycle. We'll see how. Okay. So let us remember together what are vapor power plants, what are the main components, and how we can enhance their efficiencies. So first, if we look at the overall picture, okay, we'll have several systems that are connected together. So here, if we explore the figure, let's say you have the first system is our basic system, which is relying on the conventional Rankine cycle. So as you can see, you can identify the following. So if we start by A is our boiler, okay? And in this boiler, we need to supply heat, but this heat can be of variable source. So for this system already can consider, if you want, a nuclear reactor, a fossil fuel, a system based on fossil fuel. It can be a solar system. It can be a geothermal system. That's why, as we were discussing, all of these power plants are based on Rankine cycle, because this component here, A, can be a renewable or non-renewable source of heat. Okay, so if you want, this is the source of heat. From here we have the variable possibilities. As we mentioned before, it can be based on fossil fuel combustion, coal combustion, natural gas combustion, or it can be also, it can have a source of energy, a renewable source, geothermal, solar, hydro power, wind, etc. Okay. So we can create, we know that we can create, if you want, the idea is we need a source to provide heat. Whatever the source that can be used to provide heat, okay, can be used. Maybe you can tell me for wind energy is mainly used to produce electricity. Sometimes, again, you use electricity to produce heat. So it depends on the conversions that you are using. Sometimes you go from heat to electricity, other times you go from electricity to heat, depending on if you have some heat excess somewhere in your cycle, you can use this excess to drive something else. That's why the source of heat here is very variable and can vary a lot depending on the systems that is available, and what are the types, if you want, of energy, in case of it's mechanical or electrical or thermal. So depending on the available energy that you have, you can decide if you are able to put a heat input to your boiler or not. Okay, so this is where, if you want, we can explore all different sources at this level. And what is common between all of these power plants is part B. So in part B, which is actually our Rankine system, we have the different components, which are the known components of, in your boiler, you have your boiler at the end is a heat exchanger. You are supplying energy to your boiler, and this energy will be delivered to a fluid flowing in your Rankine cycle. So in your Rankine cycle, you have a certain fluid, refrigerant, that will go over the different four components, which are the if you want, the evaporator, which will take heat at boiler level, okay, to evaporate the fluid that is passing through it, and then it will gain energy. It will gain energy in a thermal form, but this form will be converted to other forms. So as we know, we have learned in the first two chapters that we have a lot of forms of energy, and we rely on conversion of energy from one form to the other to produce what we desire. So here, let's say we need to produce electricity. This fluid, after being heated and storing a certain high amount of thermal energy, it will go through the turbine, and in this turbine, it will deliver a high work, okay? So it will produce a work. It will lead to mechanical energy of rotation of a shaft. And by the invention of electric generator, we are able to convert this mechanical energy into electricity. So at this level, if you want, you have the output. You are producing a certain electrical output. Okay. And you know that sometimes we can operate this cycle in the reversed way, as I mentioned before. You can supply electricity, okay, in order to produce heat. So just you have to do it in the reversed way. We will discuss this. So the same cycle can be used to convert heat to work, or can be used to convert work to heat, to pump heat, if you want, from a cold reservoir to a hot reservoir, as we'll discuss after. Exactly same cycle, but it will run in the opposite way. And after producing this work, okay, you need to have a cycle that will be repeated. That's why your refrigerant will pass through another heat exchanger where it will release a certain amount of heat. And we will understand this when we study the cycle. So here you have Q dot out. In this case, you can go from, let's say, from vapor or nearly saturated vapor state to compressed liquid, okay? Because you need to go through your pump that will pump, your pump will increase the pressure again, so your fluid can enter the boiler. So this is the cycle in summary, the Rankine cycle, which is the part that we'll discuss a lot in this chapter. And then at this level, here it's very important also to profit from the heat lost. So here you have Q dot out. If you don't do anything, you will lose it. So you need to extract this heat for a useful application. We'll see, for example, that you can pass by, let's say, another fluid here. Also, the condenser is like the evaporator, it's a heat exchanger. So at this level, your refrigerant will reject heat. So you can pass a certain, you can pass water, you can pass gases, etc. At this level in order to heat, let's say, for example, in case you need domestic hot water needs, you can pass by water to heat it to a certain level and then use it in homes. Okay, so in this way, this Q dot out will be useful. It will not be lost. If it's lost, this will reduce a lot the efficiency. While if you can use it somewhere else, then you can increase a lot the efficiency of your system, and you can approach very large values of efficiency. Okay. So this is, in summary, if you want the overall view of the cycles, and we'll see that mainly here at this level, what will change is mainly the source of energy. This will allow you to say, I can generate electricity using solar energy, or I can generate electricity using fossil fuels, combustion, etc. And even if you are using, let's say, combustion, okay, combustion gases will exist your system with very high temperatures. So also here it's good to apply heat recovery processes in order to benefit from, if you want, let's say, any loss of energy with due to exhaust of gases. So all of these ideas of heat recovery and combination of cycles will help to enhance the efficiencies of our systems. So here, for example, okay, they are illustrating the possibility of using a pressurized water reactor nuclear vapor power plant. So if you compare the elements, it's exactly same elements: turbine, condenser, feed water pump, boiler. But now at the boiler level, the heat source, okay, is a nuclear reactor system. So this nuclear reactor system will provide a high energy amount to the fluid passing through your boiler. And then you can use this heat input to produce electricity due at the turbine level, because you will convert at the turbine thermal energy first to mechanical energy of rotation, and then this mechanical energy of rotation of this shaft to electrical generation. Another possible source, as we discussed, is solar systems. You can use concentrating solar systems. You can use PV panels. So it depends on, we discussed a little bit, depending on the range of temperatures you need to reach, you can select the appropriate solar system to use. With concentrating solar system, you can reach high temperature, because you have tracking systems that can concentrate the solar energy and that can lead to, they can reach high temperatures that you want. For example, if you take several applications, you can use solar energy, for example, just to heat water in swimming pools. In this case, you don't need to exceed a heating of 30 degrees. While if you want to use your system for, let's say, for hot water needs, for shower, you need to reach nearly 70 degrees, because you need to kill bacteria at a certain temperature. If you want to supply a certain amount of electricity, so of course, depending on the power that you need to supply, then you decide on the system to use. Okay, so sometimes, because, for example, let's say fossil fuel or nuclear reactors are more energy intensive, okay, we can use cycles, combined cycles. So you have, let's say, a cycle working at an upper range of temperatures, and the heat loss from this cycle can be used for, let's say, as a backup, okay, to another cycle working on solar energy, for example. Okay, so it's very important to know what is the range of pressures and temperatures we are interested to work in order to determine what is the best type of thermal vapor power plant to use. Any question on this? And we also said that it's possible to use geothermal sources for our heat input. So then, for example, as you can see, always same concept. What is changing just is how we are getting heat in this heat exchanger. Okay, so a possibility is to extract hot water from, in geothermal application, when you go deeper, deep and deep, at deeper levels, the temperature is really more stable, so you can reach high temperatures. And when you extract hot water from deep levels, you can pass it by in the heat exchanger, which is your boiler, okay, where heat will be extracted from the water extracted from under the earth, and it will provide heat to the fluid or refrigerant that is moving through your Rankine cycle, through the four components, the closed cycle of your Rankine system. Okay, so as we can see, it's always A that is varying the source of energy that is making, if you want, a high number of sources of energy possible to use just with the same concept, with the same cycle, which is the Rankine cycle. Okay, so now that we understood the importance of the cycle, because it is the basic cycle for the majority of vapor power plant systems generating electricity, then of course we need to know what are the main laws to use in order to study the performance of such cycle. That's why in this chapter we introduced, of course, the first law and second law of thermodynamics, because we need them to assess the efficiency, the performance of these cycles. Okay, so the first law is really simple. It's a just application of conservation of energy through any component of our system. So it states that the network developed by a system undergoing a power cycle is equal to the net energy added by heat transfer to the system. Okay, while the second law of thermodynamics states that the thermal efficiency of a power cycle is always less than one. So practically, if you want to do the analysis of these statements, okay, so as we said, at the boiler level, what will happen? Heat is extracted from the energy source that can be solar, it can be from fossil fuels, from combustion of natural gas, etc., geothermal. So all of these sources will help into delivering heat, Q dot N, to be supplied to our fluid that is passing through the boiler, okay, which is a heat exchanger. We call it also evaporator. So where heat will be extracted by the fluid circulating in the Rankine cycle. Now, at the turbine level, as we said, we have production of work. So we have W dot turbine. And as we pass through the condenser, we have heat rejection to the outer environment, Q dot out. And finally, to repeat the cycle, okay, we need to go back to this state. So if you want, at this level, we have high pressure and relatively lower temperature. In the boiler, in general, you have P constant. So you have a high pressure level in the boiler. But what will happen is that your temperature will increase from a certain low level to high level, because you will, in general, sometimes the increase will not be very high because mainly you have change in phase, evaporation. But in case you exceeded, if you want, you have completed change in phase, you can reach higher and higher temperatures. Okay, so in general, in this system, we have increase in temperature at constant pressure, and we have change in phase. Then in the turbine, okay, in the turbine, we have production of work. So this will lead, if you want to, a certain reduction in the pressure level, because you are transforming energy in thermal and pressure form into work. And because of this, you will go back to a lower pressure level, but still, if you want your temperature or your state, okay, is not the same as it was at the inlet of the boiler. So you need to go back to the state. That's why you need to go through a condenser, let's say, in order to go from saturated vapor or mixture state, which is a combination of vapor and liquid, to saturated liquid state, in order to go through your pump, which will increase your pressure to the required level. So here in general, we have low pressure levels, low P, and we need to increase it back to the desired level in order to repeat the cycle. Okay, so we can study this component by component. What is the pressure? What is the temperature? We'll learn. Of course, the majority of you know how to do this, but we'll do a revision of this in case you don't have the required background. Don't worry about this. So we'll do complete revision, and we'll learn how to use thermodynamic tables to determine the different states 1, 2, 3, and 4, which will allow us to calculate the thermal efficiency of our power cycle. But now if we want to apply for this cycle, if we want to apply the first law of thermodynamics, okay? So what should we do then? We take for the whole cycle sum of Q dot equals to sum of W dot. Okay, so we have an input of heat at boiler level. So you have Q dot N. Someone is saying that there is too much lag. Is it the case for all students? So is the problem is from my connection or just for Rida?
It seems, Doctor, I don't know.
Dear students,
The others are facing the same problem.
Same problem. Okay, I will try to change my location. Okay, yeah, just 1 minute. Oh, okay, I will try to change my place. Is it better now? Is it
Yes,
better? Yes? You
yes.
hear me? Okay. Okay, so let us continue. So we were discussing together how we can apply the first and second law of thermodynamics to our Rankine cycle. So we just have to say that sum of Q dot is equal to sum of W dot. And you know that everything coming in for heat, okay, when you say this, for heat, everything coming in is counted as positive. So we should do plus Q dot N minus Q dot out. So this is the net, if you want, heat getting in our system. And this heat is transformed into work. So this is equal to the net work produced by the system. So at the turbine level, you have production of work. So you will put plus W dot turbine. While at the pump level, you need to supply work to operate your system. So you should do minus W dot pump. So this is how we apply the first law for the whole system. Now, we should know that it's impossible, okay, to convert heat completely into work. And this is the second statement, the second law of thermodynamics. So we can never, it's never possible, okay, to put, let's say, Q dot N and extract all of this amount at turbine. We didn't find any cycles that can do this, okay? So always here, when we study the thermal efficiency of this cycle, when we talk about the thermal efficiency of this cycle, it's, if you want, the useful power that is produced, so W dot net, okay, over the heat input, so over Q dot N. Yes, and it was observed that it's never possible to have W dot net equal to Q dot N, because you always have a certain loss of energy, okay, to another sink of heat. So you cannot, at this level, extract, whatever you do, you cannot extract Q dot N from the turbine level, okay? So this is by observation, by natural observation. It's impossible to convert heat completely into work. That's why always W dot net will be smaller than Q dot N. And from this equation, W dot net is just the difference between the work extracted at the turbine level minus the work delivered to the pump, okay? So according to this equation, W dot net can be written as Q dot N minus Q dot out. So the thermal efficiency can be written as 1 minus Q dot out over Q dot N, okay? Now, from this analysis, we can start to think about several strategies to enhance the thermal efficiency, okay? And one of the simplest strategy is to have a certain useful part from Q dot out. And instead of losing Q dot out completely, okay, if we can restore a part of it, this will increase the thermal efficiency. And for example, let's say you passed water through your condenser and you were able to extract a certain amount of heat to be delivered for domestic hot water needs, okay? Then you can say that a new overall efficiency of this combined system, which is relying on heat recovery, can be calculated, okay? So if you are able, for example, to use 90% of this Q dot out to heat water, okay? So the new efficiency, so after heat recovery, if you want, we can talk about heat recovery efficiency. Then you will have not only useful W dot net, but also you have useful heating. So you need to add to W dot net the part that you benefit from as heating, which is, let's say, 0.9 or 90% of Q dot out. Okay, times Q dot out over Q dot N. And then in the ideal case, and if you are able to restore all the energy lost Q dot out, then you can be very close to 100%, okay, as overall efficiency. So this is why heat recovery is really one of the best strategies to enhance the performance of a cycle. We have much other strategies that we'll talk about in this chapter, okay? Any question on this before we continue? Okay.
Clear.
Now, we can, in order to model this system, we can write the equation for each component separately, okay? And we know that in these systems, we work in steady state conditions. So no variation with time. So when you apply the energy balance, okay, the energy balance states that the derivative of energy with respect to time, which is 0 here because it's a steady state, okay, it's equal to summation of Q dot minus summation of W dot plus, for each component, you need to consider energy flows in and out, okay? So for example, let us consider your turbine. If you take your turbine, okay, let's say you have the inlet is 0.1, the outlet is 0.2, and you need to apply the energy balance for your turbine. So this is your control volume. Okay. Steady state, so dE by dt is 0, equal to summation of Q dot N. In general, at the turbine level, you don't have heat transfer with the surrounding. So it's well insulated. Your turbine is well insulated to avoid any heat losses. And your main purpose here is to extract heat. To extract work. Since you are extracting work, so the work is getting out, then you are losing energy in this system. Okay, you are losing it to produce a network to your environment. That's why we put minus W dot turbine. So the general equation, I will write it here, is dE by dt, which is the derivative of energy in the system. And because here it's a steady state, this term will cancel out. This term is equal to 0, is equal to sum of Q dot minus sum of W dot. And we consider that if you want, W is positive when it's produced by the system and is negative when we put it on the system. That's why we put here the minus sign, okay? So since we have considered the minus sign here, everything that is getting out will be accounted as plus, and everything that is coming in will be accounted as minus. Guys, do you hear me? Okay. Plus summation of energy fluxes. Okay. So plus summation of energy fluxes. So plus sum m dot in energy in. Okay. Because you have flows of energy transporting energy in your system, and other fluxes taking energy from your system. So minus sum of m dot out, E out. Okay. Where E is the energy per unit mass. So minus sum m dot out, E out. Let us apply this formula to our turbine. Okay. So as we said, for our turbine, it's adiabatic. Q dot is 0. You have production of work, so minus W dot turbine, because work is in energy that will leave your system. That's why we have the minus here. And we have one inlet, okay? Since we have one inlet, so we just have to, no need to do any summation. So it's plus m dot n times. What is the energy at 0.1? We have learned that the energy of a fluid is decomposed into, whenever we have an open system, okay? The enthalpy H1, and actually, if you want, always when you have an open system, you need to account the work of the pressure forces with the internal energy will be lumped in the enthalpy. And the enthalpy actually represent U, which is the internal energy, plus pressure times V, okay? So in the work here, we have work of pressure forces, but if we combine the work of pressure forces and the internal energy together, we get the enthalpy, okay? So this is the enthalpy, if you want, is a term that is coming apart from work, which is this term, work of pressure forces, and apart from the internal energy is the energy E. The total energy is decomposed into internal energy plus kinetic plus potential, okay? So when you develop your equation, you can lump together the work of pressure forces and the internal energy to have to put the enthalpy. That's why we say whenever you have an open system, okay, you will use the enthalpy here. While if you have a closed system, you will use the internal energy. Okay. So you have plus plus m dot n times h1 plus v1 square over 2 plus gz1. So this is u plus pv. This is the kinetic energy. This is gravitational energy. Okay. Now, since m dot inlet equal m dot out, because you know from continuity equation, from conservation of mass, since it's a steady state application, what is coming in, the flow rate, the mass flow rate coming in equal to the mass flow rate coming out. So we can say that m dot in equals m dot out equals to m dot. And we can take m dot into factor, okay? So we take m dot into factor, and then we do, if you want, h1 plus v1 square over 2 plus gz1 minus, because for the exit, we have minus the energy flow getting out. So minus m dot times h2 plus v2 square over 2 plus gz2, okay? And this term, H1 minus H2, is the difference in enthalpy between the inlet and the outlet. We will learn how to use thermodynamic tables to get H1 and H2, okay? In general, if they don't mention, in general, they say neglect in any of the components, neglect the variation in kinetic and potential energy. If they say this, we can cancel out these two terms because they are really small compared to the variation of enthalpy. If not, they should give us information about velocities, okay? So this is, after simplification, we get a very simple equation. So the equation for the turbine is mainly states that W dot turbine over m dot is just equal to the variation in enthalpy between the inlet and the exit. So W dot turbine over mass flow rate is H1 minus H2. Okay, and as I mentioned for you, you can physically do the interpretation of this equation. Why you have production of work? Because of the reduction of energy of your flow. That's why H1 is larger than H2. So your flow will lose energy in order to give energy to the outer environment. It will lose energy in the thermal form to provide work W dot of the turbine. Okay, so you lost if you want pressure, you lost the internal energy in order to produce a work at your turbine level. Now, we'll do the same analysis for all components of our system. So now we'll do the energy balance for the second component, which is the condenser, okay? So for the condenser, you should keep in mind that here you have heat exchange, okay? No work. So you can, sum of work is 0 for this component. And for your condenser, you are